Okay, well this video is about stationary points, section 15D from the textbook. And the first thing we need to consider is, what does stationary actually mean? It means when something is instantaneously at rest. So at a particular point, the speed, think of it as the speed being zero. Okay, it's not moving at that particular point. So let's have a look at this particular graph here. It looks like we have a function that is going up, then it's going down, it's going up, something's happening here, and then it's going up again. So if I were to ask you, when does this function seem to be stationary? Well, we go up here, we're going up, and suddenly here something seems to happen and it slows down, and then it goes down, and then over here we have something else that's special. Well, that point there and that point there, they're called stationary points. But if we keep going up here, we have here another stationary point. But this one here didn't turn around, it wasn't a turning point. This one continued all the way up there. So this one here, think of it as kind of like as if it's slowing down, but then it goes back up. So for this, I would like you to consider the sign diagram of not the function, but the derivative. What's a derivative? It's the gradient of the tangent. So if you consider any point over here, if you were to draw the tangent, would you get a positive or a negative tangent? Sorry, a positive or a negative gradient of the tangent? Well, you would get positive. Let's have a look at what happens here. And notice down here, that this is the sign diagram of the derivative. Look at that, the gradient is 0. Now the gradient is negative, it's decreasing, and now we have another stationary point. Gradient is positive in here, gradient was 0, and then goes up again. If I were to draw now the little arrows, our function was going up, then it was going down, it's going up, but here it's going up again. So how do I call this particular point there? What do I name it? Well, it has a special name, and we're going to find out in the next slide. So stationary points. Stationary points. Well, first of all, if we go back to here, stationary points, we had a stationary point there, a stationary point there, and a stationary point there. What do they all have in common? That the gradient of the tangent is 0. So here then, stationary points are those where f dash of x is equal to 0. Sorry, my slide's moving forward a little bit. Which means that a stationary point is at a stationary point the tangent is, and you write down horizontal. So they can either be a local maximum, a local minimum, or a stationary point of inflection. Let me just write this again here. When do we have a local maximum? Well, let's go back to our little slide, this one here. So if you consider, let's say, this region here, is it a maximum in that area, in that region? Yes, it is. That's what we call a local maximum. Is it the maximum? Well, does this function have a maximum? Doesn't look like it has, because if you look in this region over here, the video is playing again. If you're looking at this region here, up here, any y coordinate over there is greater than that one. So look, we can't say it's the maximum, but it's a local maximum. Just like this one here is a local minimum. So when we go back to this here, what would a local maximum look like? Well, if you draw the sign diagram of the derivative, let's say you would have whatever that value is there, doesn't really matter. But if it's a local maximum, you would need to have a plus and a minus. In other words, your function's increasing and then it's decreasing. If you have a local minimum, again, you draw the sign diagram of the derivative. And if it's a local minimum, it would have to be, let me think, if it's going down and then it's going up, it would have to be minus plus. And if it's a stationary point of inflection, it would have to have, let me just draw f dash of x there. It would have to be either the same sign, say plus plus, or it would have to have minus minus, so negative negative going down. But I would like to draw your so look, if you're, I'm assuming that you're copying this in your notes, so at any time pause the video, copy the notes, and then continue. Okay, there's something I'd like to bring to your attention. Let me just this one here, the stationary point of inflection. Why is it called stationary point of inflection and not just like your, say, like a normal point of inflection? I bring to your attention this type of graph. Let's say I have something that is concave, and then at that particular point it becomes convex. What would you call that particular point there? Did it change shape? It did. So it's a point of inflection. However, if I draw the tangent at that point, the tangent is not zero, the gradient of the tangent is not zero, the derivative is not zero, which means that it's not a stationary point. But if I have a point of inflection that looks like this, let's go and flat there, and then like that, did it change shape at that point? It did. We have concave and we have convex, but also the tangent at that point, the gradient of the tangent is zero. So it's two types of, well, it's a point with two special characteristics. It's a stationary point, but also it's a point of inflection. That's why we call it a stationary point of inflection. Next section. You might like to pause the video to have a look at what's going on in this function over here. And it's asking us to consider the following function with a restricted domain. Restricted domain, what's that about again? Well, as you can see, my function, it's not like this. It's not like it goes on forever, or that the x values can be whatever we want them to be. No. The function starts here and it ends there. Well, next question. Well, a question for you is, if I were to ask you, what is a local minimum of that function? Well, it looks like b might be a local minimum. All right. What's the local maximum of this function? Looks like perhaps d might be a local maximum. But is d the maximum? Can we find another point with a greater y coordinate? With a greater y coordinate of 9? Yes, we can. It's over there. So let's classify these points. I'm going to come back to a in a sec. So let's start with b. B is the, sorry, I'll rephrase that. B is a local minimum. I'm going to abbreviate min like that. Have a look at b. Is there any other point with a lower y coordinate of 3? And the answer is no. There's nothing lower than b, which means that b, yes, it's a local minimum, but it's also the global minimum. Global minimum. What's special about c? Is it a stationary point? Well, yeah. Looks like the gradient of the tangent would be 0. Is that a point of inflection? Well, yes. So it's a stationary, and careful how you spell the word stationary. Don't spell it like this, stationary, because that means, you're buying, that's a pencil or like a pen. Stationary, like that, and it's a stationary point of inflection. Sorry, my handwriting it's a bit tricky to write on the screen, so inflection. Okay. Let's now consider A again. Let's come back to A. A. Looks like A, we look at that coordinate of 10, and there is nothing higher than 10 for the y coordinate. So A is the global maximum. Let's look at D. Is D a global maximum? No, it's not. But In this region there, it's a local maximum. So let's write down local maximum. So what do we call points A and E? There's something special about them. Well, we call them endpoints. So also write down A and E are endpoints. Endpoints. Okay. Next one. I would like you to have a go at drawing the sign diagram of the function above that has a restricted domain. Have a go at drawing it. Pause the video now. Have a go at drawing it, and then come and check it. Okay? Pause now. Did you really pause? I hope you did. Well, let me have a go at drawing the sign diagram here. I have something special at B. The gradient at B is 0, the gradient of the tangent. So let me put the x value down here. Oh, I forgot to write down x. Let's put an x equal 1 there. Then it looks like we have another horizontal tangent there. So we put 2, another one there at 7. Okay. The function here in this region was decreasing, which means that the gradient is negative. Over here, it's increasing, positive. It's increasing there again, positive. And over here, it's decreasing. But my sign diagram is not complete. My function doesn't exist to the left of -2. I need to indicate that. So what we do is we draw one big line, draw, keep going. And now we put -2. And the same with that one. We draw a line, keep going all the way down there. We draw down here an 8. And now we shade the left of -2 and the right of 8. Okay? I'm going to now move to the next screen, which has a nicer sign diagram, which I drew earlier, which is that one. I'm really hoping I drew correctly. Yes, I did. Okay. All right. So this one's looking neater there. So my question to you now is, from the sign diagram alone of the derivative alone, can we tell what the maximum and the minimum of the function is? You know, in this case, the maximum was that point, and the minimum was that point there. That's like the maximum is 10 and the minimum is 3. Can we tell that from the sign diagram of the derivative alone? The answer is no. Because, for example, with this same sign diagram of the derivative, could I potentially have something that looks like this, perhaps? Say I have a starting point, it's going down, then it's going up, and then back up. Have a think about it. Have a look. Does my graph that I drew on the left there resemble the sign diagram? Oh, and actually, no, it doesn't. Hang on, I better do it again. So we have a point going down, then it's going up. I have a stationary point of inflection, then I'm going back up, and then it's going down. Now I think that's looking a little bit better. So in this particular case, is that still the maximum? No. I mean, that is the maximum there. Which one's the minimum? Okay, that is still the minimum. But could I have drawn my function like this, going up, and then like this, and then like that, and then down like that? Oh, my minimum is that one now. So what do we do to find the maximum and the minimum of something? Well, let's find out in the next example. This one here, we're going to come back to it later. So we're not going to do 12, we're going to do 13 now. And 13, it's asking us to find the greatest and the least value of that particular function in a restricted interval, which is this one as our restricted interval. It's asking us for the greatest, but also the least value. How do we do this? Well, if you guessed the sign diagram of the derivative, you guessed properly. So let's go and do it. We have to first find the derivative. Let me write down dy by dx equals. We have 3x squared minus 6x squared. right? No, hang on. What am I? Yes, no. 3x squared minus 12x. I think I got that right now. So 3x squared minus 12x. I would like to draw the sign diagram of my derivative. To do that, I think I'm going to factorize it to help me draw a little bit. So I'm going to factorize it with the common factor of 3x and then x minus 4. Okay. How do I draw the sign diagram of this? Well, if I look at my derivative itself is a quadratic. It's a convex quadratic. So I'm going to have a go drawing the sign diagram now. dy by dx. And I apologize if my slide moves to the next screen. Don't know what's happening. So, question. When is my derivative 0? It has two zeros. What are they? Well, when x is 0 and also 4. We said that my derivative is convex, which means the sign would be plus minus plus. Be very careful. I'm not doing the tangent of my quadratic. I'm not finding the tangent of my quadratic. Quadratic is a derivative, which means a normal sign diagram, plus minus plus, plus minus plus, which means it's going up, it's going down, and then it's going back up again. We have a restricted domain here. So we have to find the y-coordinates of not just these points here, but also the y-coordinates of my endpoints. So how would you classify that particular point? Well, it's going up and down. That would be a local maximum. This one over here, the 4, local minimum. So we have to now do what's called, we have to consider the critical values. Our starting point is -2. Let me write it there, -2. Then we have this special value 0. Then we have this other special value 4. And then we also have to put the endpoint of 5 there. Okay? How do we find the y-coordinates? All of these x values, you have to go and substitute them into the original function there. Right? So I'm going to put these in my calculator now, and you might like to just hurry this up a little bit. So you know what? I'm going to pause it, and then I'll continue. Okay, I have now found all of the y-coordinates of our critical x values by substituting them into there. We have to ask ourselves, what was the question asking us? It asked us to find the greatest and to find the least values of that particular function. We consider now all of these y-coordinates. It looks like the least value is -27. And what is the greatest value? Oh, it looks like it's 5. Okay, well, we've got a sentence now. The greatest value of y is 5, and the least is -27. Okay? Well, as always, I recommend checking our answers with a graphics calculator. So let me get my graphics calculator over here. And as you can see, I already have the function typed in there ready to go. I draw it, and I get that. First of all, I'm going to check that that the local maximum and minimum occur at 0 and 4. Let me check that. Ah, good. 0, perfect. And now go Shift G-solve minimum. Hopefully I get that one there, 4. And look at that also. I'm getting -27 there. And sorry, what was that? The y-coordinate of the max that we had here, the local max, it's 5. Oh yes, 5, that's looking good there. Well, now I also have to check the -2 and the 5. So let's go and do a shift trace. -2, I'm getting a y-coordinate of -27, perfect. That's that one there. And I'll type in 5 now. 5. And looks like I have -20. -20 there. Okay, alright. I'm going to show you something else now that you probably haven't done before. How do we restrict the domain when we're typing in the function itself? Well, what you do is we type in a comma after the function. Then we type in a square bracket, that is shift plus there. You put the starting value, comma, the ending value there, end value, and we go bracket. And now we draw it again. And look at that. We have a restricted domain. Okay. Let's now move on to example 12, which is the previous one that I had in your booklet. What is it asking us here? It's asking us to find and classify all stationary points. Not just simply to find them, but also to classify them. Well, let's do this. Let's classify these points. Hang on, stationary points. How do we find stationary points again? Derivative. Well, let's do it. Oh no, let's try this again. F dash of x is equal to 3x squared minus 6x minus 9. What do we do again? Well, we have to draw the sign diagram of this. To draw it, how about we factorize as much as we can? 3. Can I do factorize that further? Yes, we can. We can go, plus 1 and x minus 3. 3 there. Okay, let's draw the sign diagram. What type of function is our derivative? It's a quadratic. If it's quadratic, it looks like it's concave. So you have to be plus minus plus. Okay, let me draw the sign diagram then. Whoops. F dash of x. X here. What are the zeros of our derivative? They are -1 and 3. We said it's convex, so plus minus plus. As always, draw the little arrows to help us there. And it asks us to find and classify all the stationary points. So when do we have stationary points here? Well, it looks like that's a stationary point. That's a stationary point. What type of point is the point when x is -1? It's a local maximum. And this other one is a local minimum. But it's not sufficient to talk about the x. We have to talk about the points themselves. So for that, we have to find the y coordinates. The y coordinates, and we put the x values into the original function. So we have f of -1. You put into the original function, and we get 10. We do f of -22. You put into the original function, we get -22. And now we're ready to go. So we say now, therefore, -1, 10 is what type of point is -1, 10? Look at the sign diagram. It's a local maximum. And 3, -22 is a local minimum. Okay, so that concludes this lesson. Could you please go and start doing questions from section 15D, please?